Thank you everybody for joining. As I mentioned, my name is Matthew. I'm an application engineer here at Hawkridge Systems, and I'm joined by Sean Mars. And today we're going to be talking about scanning for marketing and simulations and rendering. And it's kind of an underutilized use of scans. And the reason why I mention this is because typically when we think of scan data, we think of it for like the aspect of reverse engineering, or maybe even something like inspection. But actually, rendering and simulations are useful for scan data. And the rendering aspect is actually pretty big when it comes to marketing. So we just have a brief little agenda. What we're going to do is we're going to start with a little introduction, just talking about the idea a little bit more, and then we're going to be exporting out our scan data. So I'm going to go over how we actually apply our color to a mesh to bring up for exporting and rendering. I'm going to go over a brief little rendering process, so just what goes into how we actually render our object and what kind of things we can do with something like Visualize or SOLIDWORKS Visualize. And then afterwards, Sean is going to take over. He's going to show us how we use scan data for simulations. He's got some really cool examples coming up. All right, so how is scanners being used for customer experiences? Well, we typically think, as I said, with scan data that we use it for reverse engineering and inspection, but there's actually a huge aspect when it comes to being able to show different people, like our clients and customers, or even other shops that we work with, just what to expect when it comes to what to expect with the product. And we can do this through sending a render or maybe the object itself, or like the CAD itself. But rendering is a really good way to be able to show just what a finished product would look like. So for example, we have scanners being used for the aspect of being able to run a simulation on it. So we'll scan our finished product and we can do some kind of testing on it just to see how well it would compare to the theoretical version. Or we have something like this bottom picture with something like this little statue. Toy industries use this a lot, being able to scan their products so that way they can show customers, hey, this is what you're expecting when it comes to get your product, or maybe even posting it on their website. So being able to have a 3D model in a viewable space that consumers and customers can kind of pull up on a phone, or like I said, you can send it to a different shop and they can kind of rotate it around and get a 360 view of an object with its real life kind of color and data application to it. Another really cool use that I think is really neat is being able to use scan data for product development and kind of unique accessories. So we have something like this bird skull on the bottom, and it's been turned into jewelry. And this can either be done by scanning the object and then just doing a one-to-one CAD conversion. We talked about auto surfacing at one point. But beyond that, being able to take the scan and actually just apply it to maybe a product. So if you have some kind of custom accented piece you want to add, well, you can scan that object, and then you can again place it on your part and print it out or manufacture it with that unique design. One use that is actually almost an entire industry on its own is being able to scan full body people. This is used a lot for maybe miniatures, so printing little accessories for like a wedding or some kind of get together event. But beyond that, it's having a full body scan is really helpful to be able to model around it. Medical industry uses this to be able to figure out, how does a casting sit, or the clothing industry will use this to know how we'll, having a base model to kind of work off of, being able to kind of design their clothes around it. And then again, we have that extra added benefit of, because it's a scan, and we've added in these kind of custom fits or clothes around it, well, we can just bring it in and start rendering it. If we have to swap out the body with a different person, well, then we can definitely do that really quick with a different scan. Two industries, though, that are really starting to boom when it comes to using scan data and 3D printing is the medical and museum industry. The reason why is, 3D printed parts can be much easier to touch than something like a T-Rex bone. As much as we would love to be able to hold onto a fossil and kind of pass it around, and you use it for something like education, you can't really do that because it's a fragile object. So a lot of museums are scanning their objects to put it into like a VR and AR environment. So in this case, I have this ram skull or that I can rotate around. But people like the Smithsonian are starting to scan their inventory so they can upload it to their website. They have a digital inventory in a high quality render that people can rotate around. So if you don't want to go to the museum, well, you can see what is in the museum on your computer. Being able to use CT scans in the medical industry. CT is a form of 3D scanning to scan something like a body part on an organ. So that way you can, maybe even print it out or work in a virtual environment for practice. Again, this training idea, being able to train different surgeons on, what does it look like in an augmented reality environment. Maybe we want to show, the patient what surgery we're going to perform, or I want to show a colleague what surgery we're going to perform. So I have a 3D printed object that is something more physical in representation. And again, we can also put this in kind of like a VR environment, making a render of it so we can see what it looks like in a 3D space before we actually go in and do any kind of operation. So, this is beyond just the medical and museum industry, though. A lot of manufacturers are using this to, especially the augmented reality, to know what their parts will look like in a 3D space, in a real life environment, before they actually manufacture it. If you want to swap the colors, we definitely can do that as well, working with digital assets. And the reason why, working with digital assets is so helpful for the ability to swap colors, because you can start with a very nice base. And I've said this a few times before, but kind of the raw data and the mesh data that you work with is kind of the skeleton that you'd be building off of for all future designs. So in this case, we have an Adidas shoe. This picture on the left is the one-to-one scan. This is what the finished scan looked like. I applied the color from the scanner to it. But let's say a customer says, hey, I want to see what it looks like in black, white, and gold. Well, instead of having to remanufacture the shoe or design it in whatever software I'm using for designing the shoe as a base, manufacturing it again, then taking those photos, and then I send the customer what this design looks like, just to potentially hear them say, actually, I don't like it in that color. I can do this all in a virtual environment. I can scan my shoe, so I have that high quality level of detail with the mesh, and then I can bring it into something like Substance Painter and paint over it, and then render that new painted object. So instead of even having to manufacture anything, I have a completely new design. I can show my customer. I don't have to work with any kind of physical object. And it just makes it really handy to be able to collaborate with different people. And this, again, goes beyond just working with just colors. Working with digital assets is really handy for something like sculpting. So again, being able to take, something like that bird skull and turning it into an accent piece for jewelry. Well, a lot of times you might have to manufacture something around some kind of object, or make some kind of fitting around an object. Being able to scan it and then kind of sculpt around it can really help out, instead of having to bring it in something like CAD. And then you can just color it right afterwards, so you can get a high quality render, get an idea of what your finished product will look like without even having to touch a tool at once, or a physical tool at once. It's all done in the kind of VR environment or your computer environment. So I'm using these terms like OBJ and STL and XYZ, and I'm sure you might have heard these terms before too at one point, working with different clients and colleagues. And you might say, well, what is this type of data? I'm used to kind of CAD data like SOLIDWORKS parts and solid bodies, steps, and parasolids. Well, all these different types of file, these XYZ and STL and OBJs, they're just different ways of displaying point data or mesh data. So for example, XYZ is raw point data. This is typically, if you have a laser scanner, it's what the laser scanner is going to kind of generate. It's just the points in a 3D space that haven't been triangulated or gone through triangulation, which is what we use to turn these points into a mesh. So if you ever have seen something like an STL, which is just raw mesh data, you'll see it's a bunch of triangles or facets. It's an interchangeable term. And what these facets are made from, or these triangles are made from, is just by connecting the dots, essentially, of this XYZ data. This XYZ data can come in the form of like a Excel spreadsheet, where it just has the XYZ points in a 3D space of what every individual point is. You upload that into something like SOLIDWORKS, and next thing you know, you have a bunch of points in 3D space that you can kind of work off of and get an idea of what the object will look like. Turning it into that STL, turning it and giving it those facets, allows you to add normal information. So I'm sure we've all worked with normal information, just like in SOLIDWORKS, and they kind of act the same way. These facets are individual surfaces that have been stitched together. And because of this, in this normal information, we can apply color to it. This color is what we turn that STL into an OBJ or PLY, which is essentially just mesh data that has color applied to those normal faces. So that way we can kind of get that 3D color aspect. We can see how all of our faces interact with one another and kind of go from there. OBJs have a separate PNG file for where the color and texture is stored, which can be manipulated separately, whereas something like a PLY has both the color data and the mesh data intertwined into one. So you have one single file that you can send between people. This causes it to be a little bit more larger in file size, because that information is combined. Or something like an OBJ, I can open an OBJ without the JPEG file, and I'll just have a colorless mesh data. Whereas if I had a PLY, I'm always going to have that color data. And these are used for different things. So, different file types might be better for 3D printing versus manufacturing and SOLIDWORKS, being able to get that color for reverse engineering. And, you might be wondering, well, how do I actually apply the color? Most softwares that can do triangulation, so generate a mesh from XYZ data, is also able to apply color to that mesh, because it really is just taking photos and just kind of slapping it onto the normal faces and generating our OBJ or PLY body. So I hope that kind of clarified a little bit about what these file types are for and how they are kind of used. Again, XYZ is the raw data. We triangulate it to turn it into a mesh. This is typically what we work with for reverse engineering and measurements. But if we want to go that step further and we apply texture to it, that's how we get this OBJ and PLY. So how about actually generating one of these OBJs and STLs, and how what kind of is the steps to do that? I like Artec scanners because, and especially Artec Studio, purely for the fact that, you get the high quality scan, but you also are capturing color at the same time. Typically, how we have to capture colors through photogrammetry, so taking a ton of photos and then importing in these photos into our meshing software. So kind of like a flow chart on the right side, and it seems pretty simple, but that really is the workflow in a simplified form for almost all kind of projects you can approach. You're going to generate your mesh, and then after your mesh has been generated, you're going to add in your texture photos. This might be kind of another interchangeable term, but texture really just refers to color when in the scanning realm. So we have our mesh, we add our texture photos, our color photos to the software. We then apply these textures to our mesh. So again, we have these normal faces on our triangles or facets. We're just applying that color to those normal faces. And then if everything looks good, we just save it out as our file type. And like I said, in something like Artec Studio, Artec scanners are capturing both color and geometry information at the same time. And we have like a texturing tool to be able to apply that color to our object. But this is one thing to just talk about. How about we actually show what it's like to do this? So I'm going to pull it over into Artec Studio, and I have a scan right here. It's a little switch controller, and this was made through 2 different scans. So I have these 2 different raw data points right here. And as you can see, it has all this color, and that's because if I expand out one of these frames, I have texture information, these kind of colored photos right here. Like I said, typically this will be something like I've taken with a camera itself. If I'm working in some kind of photogrammetry environment, I would take these color photos myself, and then upload them. But the key thing that, regardless of if you're using a camera or the Artec scanners, is you want to make sure you have a good coverage of color. So in this case, I look around, I can see that, okay, this side just has the top side, that's perfect. This is the top scan, it has good color spread on everything. If I were to show the second scan itself, just the bottom side, I can see that it also has a good color spread. So I can see in my preview, and if I even go to my point format, that it looks like I have my complete object covered in color. So I need this because I don't want to have any kind of in-painting color texture. Sometimes, again, if you're using something like Substance Painter or some kind of third-party tool to paint in color, you don't have to worry so much, but a lot of us are going to want to have a good spread of color across our object or our scan. At this point, I've already turned it into a mesh. So I have my mesh right here. And what I want to do now is just take the texture frames from these and kind of project them onto my mesh. Inside of Artec Studio, we have a texture tab. And in here, I can select on what mesh I want to actually apply the texture to and what frames or what scans that I actually want to be used as my, my referencing raw data for the color itself. So I'm just going to make sure everything is selected. So I choose my mesh, my 2 different scans, and then I want to set it up for an export because, again, I want to have this come out as a single texture file that I can use later on. We do have ways to normalize texture painting. Most meshing softwares have these capabilities as well to take an average of the surrounding colors and apply it to the mesh. And we can also in-paint missing textures. Something that's kind of important is the output texture size. This is going to regulate essentially the sharpness of our color. Having a medium size is really good, and we also want to make sure that our mesh size isn't too big. So I've already gone through and reduced this. I'm applying a medium level of detail to this color because it's pretty simple. And at this point, I just click apply, and it's going to go through and now put on that color to the object. I'm talking about these output texture sizes and mesh sizes, but a lot of times we get a lot of large amounts of data to work with. And most meshing softwares do have ways to reduce the mesh triangle count so we can get something a little bit lower. But the issue is if we get too low, we get too blocky and then our color doesn't apply well. Same issue can happen with the output texture size. If it gets too low, it comes out kind of pixelated. But even at this medium setting for both of them, we can see that the color comes in pretty well actually. And I can adjust the brightness if I need to, so doing some surface level of manipulation. But if everything looks good, I can just click apply. And there I have it. My file size went from about 7 megabytes to 25 megabytes because I added all that texture information. But that's okay because the points are still pretty low. We still have a relatively small amount of point data, about 314, or sorry, points, triangle data, about 314,000 triangles, which is a decent size. At this point, I can now just export out my mesh. If it, like I said, if everything looks good, I can just export it out, save it onto my, my folder. I'm just going to name it as an OBJ. And then I have this texture output format. So if I want to be a PNG or a JPEG, this is essentially what my raw texture looks like, my color looks like that's being applied to my mesh. I'll just click export. At this point, we're kind of done. I can send it over to a colleague who does rendering. They can pull it up in the rendering software and start rendering the object, get it a kind of a real life look. And what I mean by real life look is, you know, when I was doing this render, we can see that it didn't look super realistic. It was kind of like a blocky color, and it's just an overall size or an overall preview in a way. And the reason why is because rendering is where we add that realness because of lighting and the unique textures that we're going to apply to it. But again, kind of just like with working with mesh data, if we have a poor skeleton, we're going to have a poor model in the end. Same thing when it comes to rendering. So if we have a low texture size, so I chose that 2000 by 2000, but let's say I chose 500 by 500, we can see that it gets a lot more pixelated. So we have a 10K comparison to a 500 by 500 resolution comparison. You can see the difference in the two. One has, you can actually see the sharp edges of that cloth, whereas the other one is kind of pixelated. We also, if we have a smaller mesh, it applies quicker, kind of like what I mentioned earlier. That mesh was 314,000 triangles. It's a decent sized mesh, but we can probably go much lower than that. The issue, however, is that the lower we go, the blockier it's going to be. Remember back to how I said that we're kind of connecting the dots with that XYZ to when we're triangulating that XYZ to an STL. Well, if we create a smaller mesh, we're essentially reducing the number of triangles being used, so we're creating blockiness to it. This is okay for flat surfaces. You only need 2 triangles to represent a flat face, but when it comes to a sharp edge, that can cause problems. And because these are normal information that this texture is applying to, we might have sharp edges in our texture application. So these are just like the little things that you got to keep in mind when it's starting to work with mesh data. But it isn't anything too crazy, and or anything that you can't work around just off of a little bit of experience. So we got our OBJ down, we got our mesh created, we applied the color to it. Well, how about actually turning it into our render? How do we bring it into Visualize? And it's actually just as easy as it was just to kind of create our OBJ right in Artec Studio. It's just a few button clicks. I really like Visualize because it works not only with SOLIDWORKS data, so we can just take a SOLIDWORKS part and bring it into Visualize and do little bits of lighting and color application changes. But it works with any type of OBJ. And as long as our files are in the same location, it can reference it pretty well. So again, our step 1 is to reduce the polygon count to get a reasonable size. And then we apply our color to it, exporting out our OBJ, what we just did a moment ago. And at this point, we just got to place all in the same folder and bring it into Visualize. That's how do we kind of prepare the files. You can see also on the right what that texture preview will look like. So that's essentially the texture that was put onto that mesh before we exported it. We can do something called retoppling. This kind of is getting in the realm of more in the clothing industry with retoppling versus manufacturing, but helps break up this into a bit better of a layout so it's easier to manipulate later on. But how about we actually just show a little bit of the stuff we can do in Visualize instead of just kind of talking about the theories. So I'm going to open up in Visualize. I've already got the program open. This is kind of the basic user interface. And at this point, I can just go over into File, and I'm just going to import in my object. File import, going to bring me right to the folder I just saved out as, and I'm just going to select that red controller too. I'm only selecting the OBJ. I don't need to select the MTL or the JPEG file because they're already residing in here. And then you can even see I have step bodies, SOLIDWORKS part files, parasolids. They're all able to be selected and imported, so we can use all this data inside of Visualize if we want. We also have multiple objects inside of Visualize too. I'm just going to import in that red controller that we just exported out. I'm just gonna say maintain my folder structure, and it's just gonna go through a quick little load. And here we have it. It's now inside of Visualize. It's pretty simple right now, and the reason I'm also in this kind of preview render mode, so it looks kind of different than what you would expect a high quality render to look like. But that's, again, we're in this preview mode because we're going to make some changes to this. You know, maybe we want to center this object. Well, I can select on the object. You know, maybe I want to rotate it around. I can do that. I can change my scale if I want to make it bigger or smaller. Looks like I made it a little bit too big. Might reduce that down just a tiny bit. Or I can just re-import it if it's too far off. I actually might just re-import it real quick. But you know, we can do different things like scaling and adjustments. So these are all possible within Visualize. If we want to get it into like a center location, if we want to snap it to the floor, there's even what I thought was really cool, like you can do like simulation tests. So you can do drop tests and you can kind of see how it would naturally lay out on the ground, like different objects. But at this point, I can now go in and, you know, we have this basic lighting, and if I go into like a fast render mode, we can see a little bit of color. But what if we want to add something like a unique sunlight? You know, a lot of times if we're making farming equipment or manufacturing tools, we want to see what it looked like out in the field to show our customer how awesome that product is. So I can add in a sunlight environment, changing up the lighting that is being used inside Visualize. I can say where this location is on Earth, what time of day it even is, and I can adjust, you know, how bright it is, how bright is that sun, what's the rotation of the sun at this moment. And as you can see, just like with slight little changes, I took that kind of blocky preview into something that looks pretty nice with just adding in a unique sun location. Again, if you want to add this in for something like a tractor equipment, really useful that way. On top of all of this, let's say I want to switch up the material being used in Visualize. Well, Visualize is a really unique tool called split part, and it's kind of on par with that topology word that I used a little bit earlier, being able to take different parts of the mesh and break it into different areas so we can apply color to it. But splitting the part allows us to kind of do that on individual areas. So let's say I have this controller, or you know, you have your different parts, and there's a certain section you want to have shown with glass versus a matte object. Well, I can go and I can select on something like, you know, this X button, which I know is going to be plastic or a certain type of plastic, like a metallic button. But I can select on that, and I can split this off into its own identity. So at this point, after it's been split, which just finished up, I can go into my color tab, and I can take my material. Maybe I want to copy it in, so I have a second version of this material. And like I said, I can change this material. So instead of it being something like generic, I can change it to metallic paint. And I can just drag this over onto that X button. And now my X button has a metallic paint color versus the rest of the object, which is kind of like a plasticky object. We can switch this to matte. And then we have this as, you know, metallic paint. And if I pull this back a little bit more, we can kind of see that difference in the two. And I can even see a bit more what it would look like with this accurate render mode. So computer might have froze up just a tiny bit. Oh, there it goes. So I can do this accurate render mode. It's going to go through and perform a series of cycles on this, which is going to make it a kind of really high quality render. At the very end, if everything looks good, I have my camera angle set up. I can set this back into a preview to save some time or some resources and switch over and do an actual render. This render is just going to save out to a certain location. So in my case, I'm saving it out to my simulation folder. I want it to be saved as a JPEG, PNG, and I just click Start Render. Let's go through those cycles to actually create our object. So I'm just going to wait for finish because it is pretty resource intensive, but it just finished in a couple seconds, and now we have a picture that I can send off to a customer. This is just a JPEG if we want to show our customer what this will look like. But you know, it's pretty simple. We just had to do a quick little texture application, export that as that OBJ, and then once it's been exported as an OBJ, just bring it back into Visualize to create a render with just adjusting slight lighting, or maybe we want to choose the material up. Let's say I'm like, you know what, this looks good, but the customer comes back and says he actually wants the entire thing, or she wants the entire thing to be metallic paint. Well, that's okay. I can just switch this to a different preview, and maybe I can switch my button up too if I want, see what it looks like in a fast render, and then create a new render just into that customer. So that's, you know, the idea of where we're using scan data for Visualize, for rendering something, being able to take our digital assets, applying new colors to them, and then with these new colors, kind of showing what something will look like without having to manufacture it and put in some kind of VR environment if needed. But how about for simulations? We get a couple pictures right here, you know, some kind of flow sim of a giant object. We have a drop test simulation, you know, you scan an object, model a case around it and you see how the case reacts to a drop test with the solid body in there. We even have something like this comparison chart. This isn't necessarily a simulation because we didn't run a simulation on this shoe to see what the wear and tear is, but we did a comparison of a brand new shoe to a worn one. And in a way, that is a simulation. We're seeing how wear and tear affected the shoe. We're going to get a color map to see exactly where these pressure points are. Well, these are just some topics, but I am going to hand it over to Sean Mars now. And Sean, he's going to go in depth about some really cool projects that he's worked on with using scan data to with Visualize to create new objects like a new topology study and this kind of flow sim. So with that, Sean, if you want to take it away.
Alrighty, thank you, Matt. Okie dokie. So obviously, I am not in the office like Matt is. Though we are both in the Portland office, so usually we do work together for obvious reasons. Though I am at home. Matt, I also have a tapestry that you can scan that I'm going to need digital assets for. Okay. All right. So let me go ahead and show you something else other than just my ugly mug. Okay, so can you see the same slide that we were looking at before? Hear me, see me, all that good stuff?
Looks good to go.
Alrighty, so once again, my name is Sean Mars. I'm a senior applications engineer. I've been with Hawkridge Systems for the last 5 years, and I specialize in SOLIDWORKS, FEA and CFD simulations, photo rendering, so similar to the stuff that Matt was just doing, and I do lots and lots of training for all those areas. So I'm going to take you folks through a quick tour of the main simulation tools in SOLIDWORKS and give you a little look into how we can use these with our scan data. So first off, what do we mean when we say simulation? So there are multiple types of simulation tools, and all of them are attempting to give us information to help us make better decisions with our designs. So oftentimes this means using that virtual prototype that is our CAD model to not only do standard evaluations such as interference checks, but also use that CAD model to help locate structurally weak areas, make informed material choices, or predict airflow patterns that may affect cooling of electronics or the HVAC design of a building. So, and this is comes in a family of products here that are all built into SOLIDWORKS, that you are working through that same interface. So we are going to be focusing on some certain specific analysis tools here, but no matter which of the SOLIDWORKS simulation tools you're using, they all focus on allowing users to introduce design validation early in the product development process to help reduce the number of real-world prototypes that are required. So one of the most beneficial aspects of these tools is that they're all integrated into SOLIDWORKS. This means the learning curve is shorter. You don't have to learn entirely new software. The turnaround is a lot faster, so you can quickly run a study and then use those results to change your design and then continue repeating this loop without having to worry about exporting and importing into another program and setting up a simulation over and over again. And finally, you have us, Hawkridge Systems, as a partner that can train, support, and consult or mentor for all of these tools. So once again, we're going to focus on two main simulation tools. So one is just called SOLIDWORKS Simulation. That's an FEA or finite element analysis tool. And the other is called Flow Simulation, which is a CFD or computational fluid dynamics tool. So in broad terms, simulation is going to be doing structural analysis. So think, is this thing strong enough? And CFD is going to use to simulate fluid flow, so water or air or maybe something more exotic that's going through like an electronics enclosure or a pump or around the body of a car. So those are the two ones we're really looking in today. They're kind of our main simulation tools. And first, we're going to take a look at just FEA, so the SOLIDWORKS simulation. So this has a lot of studies built into it. There are based on, there's a standard version, a pro and a premium, similar to SOLIDWORKS. But these studies across these ones include, but are not limited to, helping to design for strength, So how much is this thing going to deflect? What's my factor of safety? Am I using a strong enough material? You might be looking for designing for fatigue. So designing for life, how many times can I use this assembly before it needs to be replaced or it takes permanent damage? Is this part going to be able to flex back and forth a million times without any permanent deformation? You might be looking into resonant frequencies. So is this going to have issues with the frequency of the motor it needs to support, or vibrations from other components, or from the working environment? So trying to see where those natural frequencies of any shape or assembly or part are going to be. We also have ways to analyze structures. So is like a supporting structure going to buckle under the weight it's holding? Do you need to analyze large structures made out of various beam elements such as I-beams or rectangular section, angle iron? And then we have optimization tools. So can SOLIDWORKS do some of this work for me? Can it help me find a better design? So there's two main ones. There's topology optimization, which is one of my favorite because I do a lot of 3D printing, and it just makes really cool designs that like an alien race would be designing. That's what I think in my head. But the idea is, it answers the question of, can I get the simulation tool to help me shed weight while not compromising performance? So topology is going to be reducing the model down to the material most important for transferring forces. And then from there, you can export a model for printing, or probably more commonly use it as a design guide to make traditional features. The other optimization tool would just be called optimization. And this one, on the other hand, keeps SOLIDWORKS constrained within the features you created. So you're allowing it to vary specific dimensions and materials while aiming towards a goal such as reducing the weight while maintaining a certain level of strength. Past these situations, there's more advanced areas such as nonlinear analysis. So if you have really large deformations, you need to look at the behavior after the material is yielded. So you have like permanent deformation or plastic deformation, or if you're using nonlinear materials, so rubbers, elastomers, types of plastics, and things like that. There's also dynamic studies. So this is different than frequency, which is just going to be looking at the frequency study I already mentioned. It's just looking for specifically the natural frequencies. This one is, I want to put a shock load, or I want impact, or I want to simulate vibration testing, or go through one of these certain standards or something like that. So it's a lot more advanced level. So how do we use all this information with our scan data? A really common use of scanning is for reverse engineering parts. You have a really old part, there's no drawing that exists of it, you need to recreate it. A lot of times this might mean recreating just a handful, or maybe you're getting it ready for a new production run or something like that. So one way to do it is to use simulation to help you try to improve the design. Maybe you want to make it lighter. Maybe you're trying to prevent a failure that occurred in the previous real world design. So you can set up studies that kind of pinpoint that area and then start iterating on that design. So I'm just going to show kind of a cool, fun way that that I used some information that Matt sent me. So let me jump over. All right, so I have a gear over here. So this was reverse engineered by Matt from Scan Data. So at this point, we have just standard SOLIDWORKS geometry. And then I'm going to run it through that topology study. So the general process that I run through whenever I'm doing topology study is I start with just a standard SOLIDWORKS static study. So as far as this goes, this is only on a single part. And if you're interested in looking into simulation, you should know that you already have access to specific versions of simulation and flow. They're both these express tools, so they're available in all versions of SOLIDWORKS. They are quite limited in the setup, but I actually could do pretty much this exact same setup that I used for this, a pretty simple study through this tool. Also, if you have SOLIDWORKS Premium, the highest tier version of just SOLIDWORKS, you actually have everything that, essentially everything I'm going to do right here just in this one study. So you have access to the linear static study, which is what 80% of people want. It's what that basically tells you, how strong is this thing. So I set up a pretty simple study here. And the reason why I do this is to get a benchmark to give myself constraints for that topology study and something to compare my results to. So I have something pretty simple. I have a fixture to keep this from flying off. I have some loading conditions. So this is the forces that are going to be on the gear. And you might notice I actually have torques put in on either side of the gear teeth. You might be wondering, well, why do I have that? Well, that's actually because I decided to do this in a load case with the load case manager, which is part of Simulation Professional here. And this allows me to set up multiple cases. So instead of both those forces going at once, it's going one and then the other. And I can basically look at results for either of the cases of it being all stressed on one side of the teeth or all stressed on the other. I could also, put down loads on individual teeth to be more realistic to that. But part of this is too, I'm just trying to get something to compare the topology study with. So once I have something and I have some constraints to work with, all I need to do is copy the study over. So I can copy the study over to a topology study, which is going to move all of my setup over to that study type. So I don't have to go around clicking on all these little gear teeth over again, which wouldn't be fun. Trust me, I did it the one time. And then it goes over to a topology study, which actually has a lot of the same setup. Topology is limited to one part at a time, one body that it's going to try to optimize, but you can do things such as virtual walls, bolt connectors, remote loads, and remote fixtures are all really great ways to try to replicate other parts being in there. And I can even have those load cases. So that's why I loaded every single gear tooth, is because I need it to optimize a shape that's going to be prepared for putting load on any specific gear tooth. Another good way would be finding like a cyclic symmetry and just doing a little section of the model. Now, the most important thing for topology is basically these goals and constraints. So I kept it really simple just so we could, I usually run my first one about as simple as I can go, and then start working up from there. And all I did was tell it to reduce the mass. I usually set a pretty aggressive target because in the end we'll have kind of a slider of how much we want. And then a constraint saying, well, you can't have a displacement more than this tiny millimeter amount. And that was a value I just got from running that earlier static study. The value is not super important. I'm just using it to compare the changes this makes. Other ones that are really handy, depending on what you need at the end of this, are things like preserved regions. Make sure it doesn't get rid of functional faces that you need for the part. Or if you need to make this machinable results, which you're going to see mine are not, demold directions are great. Basically say you can't use any of these little tunnels or anything like that. So when I run this, and I ran it with the load cases, it's going to optimize the shape for all of my load cases combined. So being loaded on one side of the gear teeth, being loaded on the other side, and then it gives me this crazy shape. Once again, the demold direction option is a great way to prevent things like these tunnels, these undercuts that you wouldn't be able to machine out. Though you're already machining out these gear teeth, so maybe you can do some real fancy footwork. But generally, you can add in some more of these manufacturing controls. I usually run multiple of these studies and then use results from all of them to kind of inform my decision. But if you're 3D printing it, well, you're in good shape. Just there you go. You already have it. So if you can make this, if you're fine making this in plastic, it's a one-off part, or you need a handful, or you're one of the lucky few who have metal printers, which are awesome, then you could potentially just send this right out. What I did instead was I used a hybrid modeling approach, which is pretty common in this realm of things. What that means is that I used information both from the original model and the topology model, and that allows me to have these really clean gear teeth. It lets me choose exactly what I want to keep, but I can still use like the connective tissue, if you will, of the topology study. After that, you basically just run another static study on this and then compare those displacements. You can go a step further if you want and also use this as basically as a guide for creating a more machinable design. So once again, I would generally probably run some more studies using some of those other manufacturing controls and see what my results are looking like, and then use that to kind of inform how I might make choices for making a more machinable design if that's what my end goal is. And once again, I would run another study on that. And when I say run another study, I'm just copying, whatever study I have over to this new configuration. And that way I can just really easily kind of keep setup and as much as possible, run it and have a close comparison to see how well I'm doing while using my mass properties to tell me how much weight I'm losing. Okay, so that's in the simulation study side of things. There also are just a ton of different types of studies that we could do. This is just topology is one of my favorite ones because I do a lot of 3D printing, but obviously we could be running other types of studies on this as well, like I was mentioning earlier. Okay, so let's take a look at flow simulation now. Oh, actually, real quick, before I go, I do want to talk about, because if you watch any of the other webinars, we did do stuff on this phone case here, and I would like to just mention real quick that when you are using a auto surface scan, like you see of the phone over here, auto surface is a great way to grab organic faces, and it's a really quick way to create models. But it generally creates a lot of little tiny faces. And if you're building another part out of it, like the phone case here, it's going to impart those small faces to, the phone case as well. When you go to do a normal simulation, contact between those is going to be really important to get right. So to make sure that you have it's able to slide and contact if that's the type of situation you set up. So I use a lot of the geometry analysis and check tools to try to find if there's any problem faces. Really tiny faces are going to be an issue, and this might be working with your scan guy, or maybe you are that scan person, to try to get larger surface patches and clean up the original scanned model before you start running simulations on it. So mostly the biggest concern here is when you're doing these assemblies is just getting your mesh working out correctly. And then after that, things like split lines, saving selections, and things like that can really help you add forces and contacts and fixtures into the correct areas. Okay, if anyone has any questions about that stuff, please let me know at the end here. I'm going to go on to flow simulation here. So Flow is a general purpose CFD tool, which allows us to analyze a wide variety of situations. So fluid flow through a pump, heat transfer between electrical components, and it allows us to take any 3D model, either designed in SOLIDWORKS or imported, and run that analysis and determine the fluid flow in and around the model to give us insight on a large array of parameters such as velocities, pressures, recirculation, heat transfer effects. Here we can see a bunch of internal flows that could help us determine forces present in a valve, the efficiency of mixing gases or filter media at an exhaust. And Flow has a robust turbulence model that can predict laminar or mixed flows as well. So you're getting that turbulence information, which is obviously important for things like heat transfer. So we also have external flows. So you can analyze rotating machinery, investigate interactions between liquids and gases, even export results from flow over to our FEA tool. So the two tools can work together. You can be sending fluid pressures and temperatures over and using that as loading conditions in your structural analysis. So something like this, we have this simple billboard, a big wind load, and then we send all those pressures over to simulation to find deflection on that part. So though the applications between the two tools are different, the benefits are really similar. Flow is built into SOLIDWORKS. It's easy to quickly try out many design options and iterate based on the findings. And there are special modules for electronics cooling to help simulate effects of various common electrical components. Here, it's especially with fluid flow, even real world testing can be difficult to see the granularity of what's happening in a design. This is showing the results of moving around a fan to different locations in an electronics enclosure, and you can see how much it changes the flow field, and then ultimately the effectiveness of cooling components. We also have a HVAC design module that evaluates air and gas movement in working and living environments, and includes advanced radiation modeling, comfort parameters, and a large database of building materials. There's also in the electronics module a big fan library, so all those pressure curve, the fan curves for determining the effectiveness of different manufacturers' fans. It's really nice. So how do we use all this with scan data? So a common method used in automotive accessory design is to scan vehicles and design around them. Cars are generally difficult to model and time intensive, and especially there's so many makes and models, and there's new designs being created all the time. But similarly for really old designs, that things that you can't find documentation on, and it's too organic to put a caliper on, with an approach like this, you can really easily create a large library of different models, or vehicles in this case, and then use that to design around and utilize in your simulations. So if I was going to build a bike rack and I want to see really quickly, well, what's the effect of having, one bike versus two bikes? Do I want it to be traditionally mounted or inverted? What does it look like if I put it on the back? I can just really quickly, before I design anything, just run these simulations and get a good idea. Oh, is it worth making people remove that front wheel in order to reduce drag? Is that going to affect a decision that I make? Similarly, a great way to use flow early in a design is with parametric studies. These allow you to set up a large batch of experiments that can vary dimensions of a model or flow simulation parameter, and then help you get your design off to the right start. So later in the process, you can then add more detailed analysis on maybe like a frame or the bracketing, and maybe even export that information to our FEA tool to do the old double whammy and get the stress results for, make sure that your bracketing and all that is going to be strong enough. So real quick, I just want to show you using this in setting up a flow study here with some scan data, and then I'll be all done here. Flow simulation is really nice to do stuff with scan data in, because flow doesn't really care about certain trivial things like interference or anything like that, or having really difficult meshing or anything. So this is actually just the auto surfaced body. I just have some wheels that I just extruded out through here. They're not merged or anything. I'm not worrying about it. I just kind of wanted to have them there as general size and shape. And then I can start a study. So a flow study, I usually always use the wizard tool to create any kind of study. It's really the best way to make sure you have all the basics set up. So I can grab any configuration that I want. I can use a number of unit systems that are completely customizable. So this is also really nice that if you've never used a CFD tool, there's simulation tools where you have to do all of the unit system stuff yourself, and you can't like change it throughout the study, and it's just a real pain. So this is really easy. I can set things like I want it mile an hour for velocity. I can set my analysis type. So this is really easy for stuff like this. External, exclude inside areas. I don't even have to worry about any of this other stuff like gravity or heat or anything. Grab in my project fluids. So obviously I'm going to use air, but there's a number of gases, liquids, compressible liquids, non-Newtonian fluids, things like that. Wall conditions, once again, not really a huge deal for an external study for me. And then my general initial conditions. So in this case, I would do something like I want 60 miles an hour going towards the front of the car. And I'm just using my global coordinate system to direct that. So you can see a big arrow. Then I hit finish. And the great part is with an external study like this, I'm almost done with the setup. Like basically, it's going to set up a computational domain where it's going to actually run the study. I would adjust that just to save myself computation time. So right now it's going to do this humongous cube here because it wants enough room for the flow field to stabilize and things. But you know, my car's not flying, so maybe I'll throw it down a little lower, closer to the bottom. Maybe I'm not too worried about the top. You know, one of these things that just like any other simulation tool, there's meshing involved. So the less mesh it has to do, the faster you're going to be running this. And other than that, I'm just going to set up goals. So really common, do goals for saying I want to have it monitor the average and maximum velocities overall the whole thing, or maybe I want it to check out, I want to keep track of the forces that are on the faces of here. So forces maybe in specific directions, normal forces, anything like that. Track that information for me. And then what I did was actually set this up as a parametric study. So I set it up, ran it, made it looked fine to me. So I was like, okay, I want this a bunch of times. So what I had it do is vary the dimension of where the high point on this little roof rack model is, this simple model. Where is this high point going to be? Towards the front or towards the back? And then I want to vary it through dimensions. I can use multiple parameters to vary these. I have it watch certain goals. I have it set up those parameters and run that so I can see the values of those goals. And I can even have it do things like find optimal design points. So I might have it, I want it to find where that X force is smallest. And then it can interpolate between my design points to find that value of my dimension. And then I can take any of these things and create them as projects. So creating them as projects gives me another level of control. So I spat them all out here. Gives me a whole other level of control because now I can, you know, maybe reduce mesh, get things a lot more detailed. I can look at any of my results plots. So things like this cut plot are really common. I can compare my results. So if I want to take a look at multiple of these studies side by side, I can. And if you're wondering, you know, where, you know, any of these things can just be saved out as their own little image here. And that's eventually how I got to, you know, this guy here. It's just overlaying these through and just seeing. So I have both qualitative looks at how this works. You know, I have these color plots. I can do, you know, 3-dimensional flow plots to show where, you know, these the flow is moving and things. And then I also have my quantitative results of, you know, which one has the lowest force, which one is affecting the velocity the most. And then you can use this to kind of start moving forward with the design and then come back into flow or simulation of any kind to continue checking your design as you go and help you find little mistakes, little issues, and things along those lines.
Say thank you for joining, and I hope this kind of sparked some conversation, just being able to think of ways that you might be able to use a scanner to get your product for simulation or for rendering for marketing. So hopefully it's just opening your eye to different uses of things that we traditionally think would be just for reverse engineering. Well, there's actually a lot of aspects beyond just reverse engineering with scan data. Thank you for joining.